The topic that we will be discussing today is the sequences and series of functions. Sequences and series of functions. You are aware of this thing in case of real analysis. So there are two types of convergences. Sequences of functions mean when you have like you have sequence of numbers, so does you have a sequence of functions where the terms of the sequence are functions defined on some common set. So if we consider, let me first talk about pointwise convergence. Suppose we have a Fn is a sequence of so this is a sequence of functions, but we have to, since we are dealing with complex, so we will take only those sequences which are complex valued function defined. Each function is defined on some common domain and some subset of C. So then we say that this sequence is pointwise convergent on this set D if for each set in D the sequence of complex numbers this one is the sequence of complex numbers now, because if you are computing this for each function at z, then you are getting a complex number and then you make up the sequence of that complex numbers, and if this sequence of complex numbers is convergent, so this is the definition of pointwise convergence of a sequence of functions that at each point then the corresponding sequence of complex numbers is a convergence. So what you have a sequence of complex numbers. Where is my eraser? You have a sequence of complex numbers f1, f2, f3, so on. So what you are going to calculate? You are going to calculate this sequence at each point in domain D, like Z1, Z2. At Z1 you will get F1 of Z1. So F1 of Z1 is a complex number. Similarly, F1, F2 of Z1 is a complex number. F3 of Z1 is a complex number. In this way, you get a when you take particular Z, you get a sequence of complex numbers. And similarly, if you calculate F1 at Z2, F2 at Z2, F3 at Z2, and so on. So what pointwise convergence sequence says, pointwise convergence means that for each Z, you get the sequence of these numbers. The sequence has to be convergent. This sequence another has to be convergent. Every such sequence of complex numbers that gets corresponding to every Z in D needs to be convergent. That we see that this sequence is a pointwise convergent sequence. So let's talk about an example. If we consider, let me define a sequence of complex numbers where each f and z is defined as z to power n, and each z is defined in the unit disk. Remember, unit disk is a disk whose center is 0 and radius is 1, and this is the standard notation that I have kept for a unit disk. So let us check where does it go. Look at this thing. We have this number. We have z to power n. Its modulus, I can write it as mod of z to power n. So what is this thing? Mod of z is a real number now, and this real number is a number which is whose modulus is less than 1. So since mod of z is less than 1, so you know that mod of z to power n, and this is the something from real analysis. You have proved this thing already, that whenever you have a real number which is less than 1, lies between -1 and 1, then power of that number goes to 0 as n goes to infinity. So for every whatever z you take, for each z, this it goes to 0. That is, this implies that this sequence of functions is a pointwise convergent sequence. And what is the limit? Limit is 0, whatever z you take. Whatever z you take. So I note here that this is the notation that we will be using here, or sometime we will be writing in this way also, that this sequence f and z converges to the another function, but in this case the function is 0, and we will write here as pointwise on this domain D. And in general, whenever you have a sequence, in general, when you have a sequence of functions which is pointwise convergent, that is, for each point, this limit exists. This limit exists, and this limit is always a complex number. And obviously, it is a pointwise limit. It will depend upon point. So better to if it depends on point, then you will get a function which varies with z, and this fz will also be a function, complex valued function defined on z. So pointwise limit of any sequence is a function, and so what we want to do, what we want to know about things is that if this sequence has some properties, if each function of this sequence has some mathematical property, like so each function is continuous. Suppose each function is continuous, or each function is differentiable, or and going ahead, analytic, integrable. The question that we have to address is that when then the terms of the sequence are continuous, does it imply that f, the limit, is also continuous? The question is it also continuous? Is the limit also analytic, differential? If it is differential, is it also integrable? There are in case of in case of this convergence, pointwise convergence, it is not always necessary that the limit of continuous functions is a continuous function. So in case of pointwise convergence, I must say that this is not possible. This is not possible. Even this is not possible. As far as integrability is concerned, that we can have some conditions where it is, but in case of integration, the more important question is that whether you can take limit. You have here, this is limit n goes to infinity, whether you can take this limit inside of the integral or not in case of this convergence. And in case of convergence, in case of pointwise convergence, even this is also not true. So you can get examples, and I leave it to you to find example of a sequence which is pointwise convergent. But you have to find an example of a sequence of continuous functions which is pointwise convergent, but its limit is not pointwise convergent. And similarly, you find sorry, what I said a wrong thing. What I want to tell you, what I want to find you is, you have to find a sequence of continuous functions which is pointwise convergent, but its limit is not continuous. And similarly for analytic case and this integration part. So, but we need these things because when we have to study these functions, the convergence will be helpful as to us if convergence transfers properties of the terms of the sequence to the limit function. So that what I said here is that in pointwise convergence, some of these properties are not transferred to the limit function. So we need now a stronger concept than the pointwise convergence, and the stronger concept is a uniform convergence. Uniform convergence. If we have a sequence, is a sequence of complex valued functions, on some set in C, then we say that this sequence converges uniformly, to some function f on T if there is a sequence, let me read this. There is a sequence of positive numbers, sequence epsilon n of positive numbers such that this thing holds. Fnz, mod of fnz minus f of z is less than epsilon n, for this must be true for every z in Dg. Look at this bound epsilon n of this size of this fn minus f at z. It has to be epsilon n. Corresponding to this n, we are not changing epsilon n, but we have the liberty here to change z. That means this estimate must hold for every z, and this sequence of positive numbers must converge to 0. This is a better way to write the definition of convergence, the uniform convergence of a sequence. So whenever you have this kind of setting that you are where the functions, the terms of the sequence from f are less than epsilon n for each z in D and the sequence epsilon n goes to 0, what we call this, let me mm, just these epsilon n's, we call them worst case estimators. We can take them, for example, we can also choose them to be, we can choose them, this is one of the choice, choose them as epsilon n is equal to supremum over z in D f and z minus f of z. We can choose them there. So that means sometimes it is a test, it is a good thing to check where you take the f and z minus fz and you take the supremum over the domain that your functions are defined, and check whether that supremum thing becomes small or not. If it goes to 0, then clearly yours, what you say, your sequence of these functions will be absolutely, will be uniformly convergent. And it's not difficult here, because you will have always this estimate f and z minus f of z. You know this thing is always less than its supremum z in T f and z minus fz, and you are denoting it by epsilon n, and it goes to 0. So this is sometime good way to check. And now we will see that the properties that are missed by pointwise convergence to transfer, then those properties, not all I will see here, because analyticity we will not see here, and for analyticity we require other results that we will see in subsequent chapters. But yes, continuity and this integration part we will see here. But before that, the example that I just mentioned to you in case of pointwise convergence was this sequence of Zn, and Z was the member of unit disk. We just see that this is pointwise convergent. This was pointwise convergent, but it is not uniformly convergent. But it is not uniformly convergent. Why? Because you get this thing. You take epsilon n to be maximum for supremum. You just write supremum. That is better thing. Supremum mod z less than 1, z to power n. But the maximum of this thing is 1 here. So in case of this estimate, you will never have this, since it is 1 and it never goes to 0. It never goes to 0 whatever n you take. So that in this case you will never have this thing supremum of mod z and minus limit function, because the pointwise limit function was 0, to so here it cannot be something different. Mod z less than 1, this will never go to 0. So this will never go to 0, hence this sequence is not uniformly convergent. But what is the relation between uniform convergence and pointwise convergence? You can see from the definition, it is very clear that uniform convergence always implies pointwise convergence. Why it implies? Because you have this relation f and z minus fz is less than epsilon n, and this is true for every z in D. So, but domain D. So if you fix some z, pointwise convergence is that you have to look at each point separately. If you fix z in D, still this estimate holds. Still आपके पास you will have this f and z minus f of z less than epsilon n, and it goes to 0 as n goes to infinity. As n goes to infinity, that is at z, f and z will converge to f of z as n goes to So this is the pointwise convergence. But the other way, it is not true, as this example clearly tells you, because this is the example where you don't have a uniform convergence, but you have the pointwise convergence. So coming to this theorem part, let me state first thing that if Fn is a sequence of continuous functions on D subset of C such that this sequence converges to another function f uniformly on D, then the limit function, which is f, is also continuous. I'm not writing its proof. Why I'm not writing it? You have to reproduce the proof here, because the proof that you did for uh, real sequences in your previous semester will work for this also, because there is nothing special about being functions of complex valued functions or real valued functions. The proof will be same, because there is a standard proof for any metric spaces. So you have two C and R are two particular metric spaces, and the proof works exactly the same proof will work for this theorem also. So that's why we don't need to write the proof, but you need to know that proof. You can reproduce on your notebooks that proof from your previous semester notes. Whereas the next theorem, where the integration is involved, the proof of that will be written to you, will be explained to you, because it involves new things. Most importantly, what is new there is the concept of integration, because integration in case of real numbers is defined in a different way than the integration in complex analysis. So here is the next theorem. What it says that if Fn is a sequence of continuous functions on some set D in C such that I'm not taking D. Why to take is D? And let me take, because have to deal with the integration. Let's take only the contour, and a contour C in the complex plane. This is defined in C such that this sequence converges to function f uniformly on C, then it says that the limit n tending to infinity integral of each term of the sequence is equal to the integral of the limit function of the sequence. This is the context of this theorem, that here you can take limit from inside to outside, or the corresponding sequence of integrals is convergent. So let me explain this proof. I will write this proof for you. First, let's set the terms that we have to use. What is given to us is that this sequence is uniformly convergent, and since this sequence is a uniformly convergent sequence, so by definition of uniform convergence, we can choose. We can choose a sequence of positive numbers epsilon n such that this sequence epsilon n goes to 0 as n goes to infinity, and fnz minus f of z is less than or equal to epsilon n for all z in C. So this is the definition of uniform convergence. Since it is given to us, I just wrote the thing here. So C is a contour, and we can calculate its length, and let L be the length of contour C. And what is the length of the contour C? Contour C का length ये होता है mod dz, और अगर आपके पास कंटूर इस तरीके से गिवन है, अगर पैरामीटराइज फॉर्म में गिवन है, तो इट हैज टू बी, if it is xt plus iyt over some interval a less than or equal to t less than or equal to b, तो इसका लेंथ होता है, it has to be a to b mod z prime t dt. But I'm not writing parameterization because we are not going to use anywhere this parameterization. So this is, let this be the length. Now let us look at this thing. Integral fnz dz over contour C minus f of z dz. We don't need to worry about whether the integrals of these functions exist, because I'm taking the sequence of continuous functions, and f will also be a continuous function from the previous theorem. So continuous functions are always integrable functions. Since in definition where I defined line integral to you, even we didn't took the continuous function, we just took the the piecewise continuous function. So continuity is stronger than the piecewise continuity. So let us calculate this estimate, because for the convergence we need this estimate go to 0 as n goes to infinity, and that will establish the convergence of this sequence of integrals. So since integral is a linear thing, so I can write separately it as integral over C fn and z minus f of z dz. And now you remember the property that when the modulus is taken inside, it becomes less than or equal to integral over C mod fn z minus f of z mod of dz. This is the property that we discussed in yesterday's lecture. And now say if we have this thing given to us, we have this estimate, we have a bound, epsilon n is a bound of this fn z minus fz. So this is less than or equal to epsilon n integral c mod dz. So this left, what is left here is this thing. This is the length of this arc curve C. So I can write it to be epsilon n L. So this is the ML estimate actually I'm using here, that was discussed to you yesterday. So that means you have this final estimate, that is you have this thing fnz integral over C dz minus integral C fz dz. This thing is less than or equal to epsilon n L. So whatever I don't need to mention that where z belongs to, because it has been covered over all of the contour C under integration, and this is true for every n. And now by hypothesis, by definition of the epsilon n goes to 0. But L is a constant, L is not going to change. C is a fixed curve, you are not changing it, so its length is not changing. So epsilon n times L will also go to 0 as n goes to infinity. So what it implies, if your right hand side is going to 0, that means your left hand side will also go to 0. That means limit n fnz dz minus fz dz integral, this goes to 0 as n goes to 0. But this is nothing but this is just the thing that this sequence of integrals of each terms of the sequence of functions is convergent. It is given by the limit of this function sequence is given by this thing. So this was the context. This was and it doesn't require much effort. The only thing was just the single use of a ML estimate. So I pause here for a minute, and if you have any query, I can address that for a while before going to the next thing, that is the series of functions and an important test about the uniform convergence of series of functions, that is the Weierstrass M test. So you have a question, so please ask.
Yes, so
Bolo.
how can we, so in simple language, how can we differentiate between the pointwise and the uniform convergence?
Okay, just see, look at this sequence, that this sequence f and z, z to power n. In the beginning, I told you that this is a pointwise convergent sequence. Pointwise word means that the convergence depends on points. The first thing that the word explains to you is the pointwise convergence means the sequence convergence of the sequence depends on points, whereas the uniform in the uniform convergence, the convergence doesn't depend upon the points. But let me first let me first differentiate how make clear things here. This is a pointwise convergent sequence. I can write it as mod z to power n. And since mod z is a real number, and you know, in case of real numbers, in case of real sequences, a to power n goes to 0 if mod of a is less than 1, or you just a is a positive number, you just say that a is less than 1. So because of this thing, for each fixed z, this will go to 0. I'm not saying that for every z it is uniformly going to 0. For each fixed z, it's going to 0. Simultaneously, for all z, it will not go to 0. Why it will not go to 0? Because if you look at this thing, here it is depending upon point. If you take a particular z, then it goes to 0. But if you treat this as a function and you take supremum of this function, whereas the supremum of this function, supremum of this function, supremum of this function is 1. So what you needed to have the uniform convergence के लिए आपको ये चाहिए था कि जो आपके पास worst case estimators होते हैं, epsilon n you choose this supremum of जो भी आपके पास pointwise function pointwise limit होती है, but here the pointwise limit is 0, so it is only z to power n. Actually this is supremum of mod z n. And for the uniform convergence, we required this thing that f and z minus f of z must have been less than epsilon n, and the supremum is a possible worst case estimator. But in this case, we had this thing f and z, which is fz was 0. It was what else it was? It was mod z to power n. It is equal to mod z to power n, and it is less than or equal to epsilon n. This is less than already from its supremum, but the supremum is 1. This worst case estimators do not go to 0. That means you do not get the estimators. You do not get, by definition of uniform convergence, you cannot find you cannot find these epsilon n's going to 0 and you at the same time you have this estimate fz minus fz less than epsilon n. There is another way to talk about pointwise convergence and the what you say this uniform convergence also, the classical way. Let me tell that to you also. When I say that this sequence f and z converges to fz pointwise, by classical definition, it means that for every epsilon bigger than 0, there exists some, and depending upon epsilon and z greater than 0, this is a natural number such that you will have this thing f and z minus f of z less than epsilon for all n bigger than or equal to n epsilon and z. So here the dependence of this stage from onward, from which you have this f and z minus z less than epsilon, it depends upon z. That means when you change the z, this number may change. Whereas in case of uniform convergence, when you say that the sequence is uniformly convergent, this is uniformly convergent. What happens here? Here happens for each epsilon greater than 0, there exists a number and depends on only epsilon. It depends only on epsilon. It doesn't depend here. The dependence is not on z. You can take any z on the on which on the domain where the function is defined. Then you have this inequality is less than epsilon. So since here z has no relevance, here z has no relevance, this n doesn't depend upon z. So I can write here that supremum of this f and z minus fz, because this is true for every z, is less than or equal to is less than epsilon. Indeed, I can make it less than epsilon. And these are the estimators that जो मैंने definition में वहाँ पर बताए थे कि which we can choose it to be epsilon n. This epsilon n is less than epsilon, and since epsilon is an arbitrary number, and I can take epsilon to be any number. I have the choice. It just needs to be positive number, and this is an arbitrary, and there is a concept, and not a concept. Now coming back to since this is a sequence of positive numbers, and this sequence of positive numbers is less than epsilon for every n bigger than or equal to n epsilon. So by the convergence of the definition, this epsilon n sequence will go to 0. So there is sometimes while you begin, maybe you do not observe the differences, and once if you cannot make up the difference from the definitions, then what is the best thing that you can keep in mind to know what is the difference between pointwise and uniform convergence is the theorem that I explained to you, the proof of which I gave to you, and the continuity वाली theorem जो जिसमें आपके पास uniform convergence में continuous functions का limit function भी continuous होता है, whereas in case of pointwise convergence आपके पास जो कंटिन्यूस फंक्शंस हैं उनका लिमिट जरूरी नहीं है कंटिन्यूस है, और उसके लिए यू हैव टू वर्क आउट एन एग्जांपल दैट जो आपके पास प्रीवियस सेमेस्टर के नोट्स पे इजीली अवेलेबल है. तो जब आप एग्जांपल्स करते जाएंगे और ज्यादा चीजें करते जाएंगे तो ऑब्वियसली वो फर्क क्लियर होता जाएगा. जब आपके पास एक एग्जांपल अवेलेबल है सीक्वेंस ऑफ कंटिन्यूस फंक्शंस की जो पॉइंट वाइज कन्वर्जेंट है, लेकिन उसका जो आपके पास लिमिट फंक्शन है वो कंटिन्यूअस नहीं है, तो वहां से वो क्लियर हो जाता है आपके पास के वो यूनिफॉर्मली कन्वर्जेंट नहीं है, क्योंकि यूनिफॉर्म कन्वर्जेंट होती तो उसका लिमिट फंक्शन भी कंटिन्यूअस फंक्शन होता था. ओके, एनी अदर क्वेश्चन? Any other, someone else? So if there is no question, then let me check whether okay. So the next thing after sequence of functions, there is a series of functions. I'm not explaining what is a series of functions because you already know what is a series of numbers. So series of function is nothing but something like this, where the summation can be from 1 to infinity or 0 to infinity, whatever you take. It depends. Sometime you might take summation from 10 to infinity also, but it's a series. The way to write series of a function is where g and z is a function defined on some set in C. So corresponding to series of function, we define a sequence of partial sums. How do you define a sequence of partial sums? The term of each term, the terms of the sequence of partial sums are defined as k from 0 to n. It is gk. You take the sum of first n terms. In this way. So you define this sequence. So what you do, given a series of functions, you associate a sequence of functions with that, and then the convergence depends upon that sequence which we are associating to this series, and the sequence that we are associating is nothing but a sequence of partial sums of that series. And then we say that this series G and Z is pointwise convergent, pointwise convergent if this sequence of partial sums is pointwise convergent. And similarly, we say that this series of functions is uniformly convergent if its sequence of partial sums is uniformly convergent. So there is nothing to worry about that. What is how to define the sequence convergence of series? You just have to define. You just have to compute the sequence of partial sums, and that if that sequence converges, the series will also converge. If it doesn't converge, then we say that series is divergent. So obviously, all the properties under uniform convergence, like continuity and integration, is preserved, because again the convergence of a series is related to the convergence of a sequence, because if each function of this series is continuous, then this each term of the partial sums will also be continuous, because this is a finite sum of continuous functions, and sum of continuous functions is a continuous. So S and Z will be a continuous function, and if series is uniformly convergent, means S and Z sequence is uniformly convergent, and so the limit will be a what you say continuous function. Again, in case of pointwise convergence of series also, you may not have the preservance of uh, continuity and that interchange of integral and uh, summation here in case. And the limit of this series, the limit of this infinite series is denoted by this infinite sum. Okay, but what is new thing that we are going to give to you here is a Weierstrass test, which is a test which tests the convergence, uniform convergence of a given series. So I will state it here. It is Weierstrass test. But it says that suppose you have positive non-negative numbers, and the series formed by these negative numbers, non-negative numbers, is convergent. Now, if Gn are complex valued functions defined on some set in C, such that modulus of each G and Z is less than or equal to Mn for all Z in T, then the series of these functions is uniformly convergent on D. This is so simple. It is a kind of comparison test, but it is a much stronger comparison test. You just have to check whether each term of the sequence is bounded by some number, and the series formed by those numbers must be convergent, then the sequence series formed by the function is uniformly convergent. So let us check whether they what was the proof. Let's write its proof. So let me fix some z naught in D, and then we have, since hypothesis is true for every z in D, so in particular I will have this for this z naught also, that modulus will be less than or equal to mn. And so now look at these two series. I have a series of numbers. This is also a series of real numbers. Modulus z naught is a fix, and I have another series mn. So by hypothesis, it is given that this series of mn's is convergent, and this number modulus of g and z naught is less than or equal to mn. So you remember the comparison test. So by comparison test, what I get, that this series is also convergent. This is convergent, and when you write it in modulus, you say that it is absolutely convergent, but you just write first that it is the convergent, because this series mn's is series of mn's is convergent, and you have this inequality also. You have this inequality also. So what I can say now, that z naught was an arbitrary number, that means I can say that uh, this series of functions Zn is absolutely convergent. Absolutely convergent, absolutely convergent, but it is pointwise convergent. Absolutely convergent for each Z in D. This is absolutely convergent. You remember absolute convergence when you take the modulus of the terms, then that is the absolute convergence. So if it is absolute convergence, and the relation between convergence and the absolute convergence is that absolute convergence implies convergence. So this is pointwise convergent, is pointwise convergent. So at least we got to know that this is a pointwise convergent sequence. So we need to what do we need to, we need to establish now that it's a uniformly convergent sequence. And if it's a pointwise convergent, so let us denote its limit by let us denote its limit g by gz. This is a function. Let me denote its limit, because it is pointwise convergent for z in D. Now I have to show that this series converges uniformly to Gz, and to show that it converges uniformly to Gz, what I need to show, I need to show that its corresponding sequence of partial sums converges uniformly to Gz. Let's do this thing. So what we are going to do now, what I have to do, I have to find out this estimate for this. I have to find a kind of worst case estimator, you can also call. So look at this thing. What it will be? It will be gz is what? Gz is n from, yeah, you just write it, k from 0 to infinity. It is g of kz minus what is snz? Snz is k from 0 to n, and it is gk of z. So some first k terms are cancelled. So what you are left with? You are left with gk of k from n plus 1 onward to infinity z, and now I can use for each z the inequality, previous inequality, where it is less than or equal to, because it's pointwise convergent sequence, it is k n plus 1 to infinity mod of gkz. But by hypothesis, each gkz is less than or equal to mk, so it has to be n plus 1 to infinity, it has to be mk. Now, since mk is convergent, this is convergent sequence, this is by hypothesis, so there is an essential condition of convergence of a series of positive numbers, that then this limit n goes to infinity, summation k equals to n plus 1 mk goes to 0. This is a condition. This follows. This is one of the uh, result from the say, convergence of the series of positive numbers that you can see from the L analysis. If you have forgotten it, if you haven't, then it's good. Then it is good to understand this result also. So if we put epsilon n equals to k equals to n plus 1 mk, that means from this above line what we get that this epsilon n goes to 0 as n goes to infinity. So we have these estimators, and now let us plug in these estimators in this inequality gz minus snz. We had this thing less than or equal to summation mk, where k is equal to n plus 1 to infinity, and this is true for every z. There is no dependence on z. Z कुछ particular होगा. This is uniformly true for every z in D. And here I'm taking this to be epsilon n, which implies that now writing in the form of definition, I have s and z less than or equal to epsilon n, and it goes to 0 as n goes to infinity for each z in T. And as I have defined the definition of uniform, as I have explained the definition of uniform convergence, from that it follows that this implies nothing but this implies that this sequence S and Z converges to this sequence G, this number Gz uniformly on T. And this is a sequence of partial sums. When sequence of partial sums converges, it implies that the series converges. Gn is uniformly convergent. So you will get, I have explained an example of geometric series uh, which converges pointwise but which do not converge uniformly on the unit disk. You can see that from the notes also. So I will stop here, but I will take few questions if you have. Do you have any question?
No, sir.
बोलो कोई और. So okay, if you have any query anytime, and you can ask in Telegram also. So I think I must stop now.